Welcome all to this 14th lecture of Principles of Statistics. Today we're going to start a new section of the course that is called Decision Theory. So this is a more general framework than we've been considering for, general inferential procedures. And by sort of going more abstract, what we're going to be able to do is to say more things about these inference or inferential procedures. So let's start with this. It will occupy our time in the next few lectures, this whole section. So I think this should be the fourth section. So this is decision theory. And so let's just give a few definitions. So let's consider an observation. So we could be talking about sample or not. So generally we may just think of one observation. So consider an observation capital X, and this is, as usual, going to come from a model, statistical model. So from a statistical model, have theta indexed by some capital theta, and this is of PDFs, PMFs, which are of course on a sample space, on a sample space calligraphic X. Well, let's see if I manage to get it. Something like that. Okay, so so we're going to have, in decision theory, what we're going to have is decision problems. Okay, and for that, also to solve them, we'll need decision rules. Yeah. Okay, so in a decision problem, okay, so we are going to consider, in addition to this sample space, we need an action space. Okay, so this is the space in which the decisions are going to happen. So we consider an action space. Okay, and we call this calligraphic A. And we need, as I said before, a decision rule. And so this is going to be a mapping delta. So maybe just write it a bit more carefully. So this is delta going from, from the sample space to the decision space, the action space. And, even though I'm not really going to go into details of this, we need it to be measurable. Yeah? So the reason why I don't want to go into details of this is because, for measurability, of course, we need sigma algebras, but this calligraphic A or action space is abstract to start with. So we could just equip it with a sigma algebra, but then, we're not really concerned with these things in this course. And the examples that we're going to see, the sigma algebras, it would take us maybe a bit of time for at least one of them to sort of define them. So it's not really the point of this course. Yeah. So, okay. But just know that, you need measurability so that then we can take Lebesgue integral, as usual. Okay. So let's give some examples of this. So first of all, so we should be thinking of decisions, right? So what kind of, what is the simplest decision that we've seen so far? Well, that in which we have two options, right? So this is what is called a binary decision problem. So let me shorten decision as DEC, yeah? Binary decision problem. Okay, just simply because it's going to appear in a lot of places, okay? So, such as a test with the usual, null space versus, or null hypothesis versus the alternative, right? Okay, and remember we need a decision rule, so we're going to take this delta x, okay? So it's going to be a test or 0-1 decision, yeah? Because it could be that, even though it is essentially the same thing as a test, we may not have exactly testing in mind, yeah? So it may just be a 0-1 decision, yeah? Okay, so a second example, well, you can generalize this to any finite number, so let's just write that. Any finite number of options for your decision, so for m in the natural numbers, and so then this is what is called a finite multiple decision problem. Okay. Okay, and we could be saying that, okay, so I think the extension for delta is just trivial, yeah? It's cosmetic. Okay, so then 3, let's get something a bit more complicated that we've also seen. So we can take this action space to be the parameter space, okay? In which case, what do we have? Well, this is just the usual or a usual estimation problem, right? I could have written decision problem. Yeah. Okay, so this is an estimation problem in which, of course, as usual, we're going to take delta x to be some estimator of the theta. Yeah. Okay, and then another example that we've seen is essentially confidence sets. So where would a confidence set take values? Well, it takes it in the set of all of the subsets of this capital theta, right? And so, as I just said, this is a set estimation. So I just said a confidence set. Let me go back to this thing that I was just writing. So confidence set problem or decision problem. Well, actually, before doing that, let me say confidence set or set estimation decision problem. Yeah. So just as before with the test, it could be that, what we have in mind is not exactly a confidence set, but rather, some estimation of some set. And so then we fall into this realm as well, right? And so for this example, well, this delta x is going to be the usual cx, right? So our usual confidence sets. Yeah. Okay, so these are some examples of decision rules. Now, if you have a decision rule, then you want to assess how good it is, right? So how do we do that? Well, the performance of a decision rule is measured or assessed. Yeah, maybe let's say assessed via a so-called loss function. And so this is going to be a mapping that goes from our action space, right? So we're going to want to assess again the performance of a delta, and delta will be taking values in the action space. But also we need to compare it to something, right? And this something may very well depend on, and it will generally depend on the capital theta, because we're trying to, because by assessing the performance, what we're saying is, how good is this? And being good in, a very vague sense should always depend on, the parameter that is giving rise to data, because that will tell us, in the case of an estimator, for instance, well, you want to approximate that theta, right? And so on. Yeah. Okay. So let's give then some examples of these loss functions. Some examples. And okay, so in a test problem, testing decision problem, just so that we now add the decision here. Oh no, we had it anyway. Okay, so in a testing problem, what we can do is just to count the number of incorrect sort of decisions, for instance. Incorrect decision by, by taking, for instance, theta. So this is going to be just an indicator. Okay, maybe I don't want to. Okay, let's just write. Let's see what comes out of this. So we'd have a delta, that is not equal to some a theta. Okay, and where this a theta is the correct decision given that x follows p theta. Okay, so again, just to emphasize the importance of the loss function depending for the loss function to depend on this parameter, because of course, if you want to assess how good something is, then you need to compare it to some sort of ground truth. Yeah. Okay. So second example. So we can have very common loss functions are the following. So we have a delta, a theta, and we're going to take this to be the difference in absolute value, or we could also take the difference squared. Yeah. Okay, so this is what is called the absolute, like this, absolute, or, and this is respectively, of course, or squared loss. Yeah. Function. There's the function or error. Okay, right. So let's now give a definition. Now that we have decisions and loss functions. Okay, so definition one. So the risk function or simply, okay, that's not, God, okay, so function or simply risk. By the way, if you're still not finding my writing very clear, let me know. Be free to let me know. Okay, so of a decision rule, and this is of course for a loss function, right? L, and also given that x comes from p theta, is the following expression. So we call it R, so R of delta, and then of course it will depend on the theta as well. And this is going to be the expectation on the p theta of the loss function. Of the decision and of the parameter. Okay. So just to write this out in the continuous case, so again, you can write this for the discrete case, and I leave it for you to do so. So this is going to be now, so that's lowercase now, x theta, and we're going to integrate, as I was saying, with respect to x theta dx. Okay, so this is the risk, and let me then, talk a bit about, because it depends on the laws. So then let's just, and the decision that will be taken. So let's just carry on with examples. Okay, so the expectation and the theta of delta x minus theta squared, okay, so this is the squared error, is so the so-called quadratic risk. Okay, and this is of course of delta. So when we have, so this is, essentially an estimation problem. So let's just clarify that. So when this calligraphic A is our parameter space, and, and delta is an estimator, of theta, then this quadratic risk is called, so it is called, yes, it is called the mean squared error. Which generally you will see shortened as MSE. And this is of the estimator. Okay, so second example. So let me just write I here first, and then second. Okay, so second is, let's look at testing. So we can take the expectation of the the loss function that we were considering. So this being distinct from some a theta. And this gives, so depending on the theta value, this gives the so-called type 1 and type 2 errors. Okay, so far everything we've said is sort of, it has some sort of frequentist flavor, because we've always said, this given x distributed according to some p theta, and then we've sort of written everything in terms of the theta. But we can also, introduce the Bayesian framework in here, and so it should be quite obvious what's going to happen, right? Because now, if we consider theta as being random, then we want to integrate these things with respect to the prior. Yeah. Okay, so let's talk about then Bayes rules. So Bayes rules for risk minimization. Yeah. Okay. So definition. So given a prior pi, and this is on parameter space, of course, the so-called base risk and of course this is implicitly for a given loss function, capital L, and this should be of some delta, is given by the following. So we have here R pi of delta. Yeah, this is how we're going to denote it. And so now note that we've sort of lost this theta dependence and sort of swapped it by the prior dependence. And so this is going to be now the integral over the parameter space, you know, what I was saying before, right, of the risk. Okay, right. So this is one thing that we defined, and then let me also define the so-called posterior risk. So the posterior risk, okay, is given by what you probably expecting, which is is just simply that, it's just simply the expectation on the posterior. Okay, and how can we denote that? Well, I could just write here brackets dot and then condition on the x, or another way of another common way of writing this in textbooks and the literature is just writing the conditioning inside. Yeah? The expectation. So what is this? Well, this is just simply the integral over the parameter space again of the loss function. So of the loss function. So let me just check that I haven't written anything silly. Yes, okay. So yeah, of the loss function of the two guys here. Now theta, and as I was saying, we're going to integrate now with respect to the posterior rather than the prior. Yeah? Okay, and let's say, because we want to minimize the risk, so then let's define lastly a pi base rule. And then many times we'll omit this pi. So a pi base decision rule. This is again, we'll omit the decision bit. So what is this? Well, this is going to be, we can note it as delta pi. This is going to be a minimizer, okay, of this base risk. So is any decision rule minimizing precisely the R pi delta. Yeah. Let me just write delta. Let me just write a dot. So that's the function we're minimizing. Yeah? Okay, so let me make a claim now. How do we connect the base risk to the posterior risk, or is there any relationship? Well, very likely there is, right? Maybe I can leave it there for you to see it. So let's put it there. So let's make a claim. Okay, so I claim that, if you have let me just write, first of all, a delta. So let's say, if delta minimizes the posterior risk, okay, by which I mean that this guy, so L, delta, and theta given x, and this is delta, delta, so this is less or equal or less than or equal to L delta prime theta given x, and this is for all delta prime and x as well, yeah. Okay, so this would be, sorry, x, yeah, it would be for every x, by which I don't mean, in terms of the posterior, but rather, in terms of the elements that it takes, yeah. Okay, so then the claim is that the base risk is actually going to be minimized, yeah, by this delta. May not be the only one, but it is a minimizer, yeah. Okay, so how do we show this? Well, I mean, the argument is very simple. So indeed, what we have is that the R pi of delta is going to be equal to the integral over the parameter space over and then another integral over the sample space of the loss function. That would be lowercase that capital X theta. And so firstly, we integrate with respect to the PDF. Okay, so the X, and then we're going to integrate with respect to the prior just by the definition, right? Okay, so once we have this, let me note that the combination of these two, right, as a product, will give us pretty much the posterior distribution. Okay, so this is going to be P theta given X, but we don't have the normalizing constant, so then we just multiply by it. Yeah? And so this is the integral of this by theta d theta. Yeah? And let me call this constant mx. Okay. All right. So what we get here then is just simply the expectation or the integral over the sample space of the expectation and the posterior of our loss function theta, and is given x. Okay, so that's a bit, in this case, is a bit unnecessary, but anyway, just so that we sort of fall within the framework of conditional expectation, or at least the writing of it. Okay, so this is going to be this quantity, and so what we see here is an expectation of a non-negative quantity integrated with respect to a non-negative quantity. Yeah, so that's just so that just gives the result. Yeah? So where both not delta, sorry, the loss function and the m are greater than or equal to 0. Yeah? Okay, so that shows that justifies the claim. And so in words, what we get is that, so thus, or a minimizer of this posterior, let's maybe make it explicit for now, so this pi posterior risk is, or minimizes the pi base risk. Okay, good. So let's say now something new, which is actually an important result. So you'll be using this in other courses. So you're going to show the following, yeah? In the example sheet, and is that the unique pi base risk, okay. Sorry, not risk, rule, and this is for the quadratic risk, and let me also say for the absolute risk, is the posterior mean. And so for the absolute risk is not the posterior mean, but rather instead the median. Yeah. Okay, so posterior mean, I write it as the expectation under the pi of the theta given the x, right? So that's the notation that we're using now. Yeah. Okay, so this, this gives us the following result, actually. So theorem 1 of this section, so let's take a decision rule. So let delta x be unbiased, okay? For theta, i.e., what I mean is that the expectation under the p theta of this delta is going to be precisely the theta, yeah? And this is for all theta in the parameter space. Okay, so we've taken it, we've taken this estimator to be unbiased. So if delta is a pi base rule, okay, and this is for the quadratic risk, and of course for some prior, yeah. So for the quadratic risk, then what do we have? Well, we get that the expectation, and this now is with respect to both the data and the parameter, so the expectation of delta x minus theta squared, so this is now related to the quadratic risk, is the integral of the parameter space of the of this quantity. So this is the expectation with respect to the p theta, and of this guy minus theta. So we go in parts, basically as in this is what is called the tower rule, right? We haven't really done anything here. So the result says, what the result is saying is not the first equality, but rather the second equality. Yeah? So it says that this expected value is actually going to be 0. Yeah? And in particular, what we get, so because the quantity that we take in the, the square, is always non-negative, what we get is that delta x is going to be theta, and this is with probability 1, but we need to specify with what, with respect to what probability distribution. So this is the fx theta pi theta distribution. Yeah? Okay, so probability 1 with respect to the posterior, essentially. Yeah? So it's the unnormalized posterior. Okay, so let's prove this. It's actually, again, quite a simple proof. So if we take, the quantity that we want to analyze squared, and we just simply, look at its value, then we can expand the square and get that, what we have here is this, minus 2 times the expectation of a product, theta, plus the expectation of theta squared. Yeah, so remember, the expectation is both over or with respect to the distribution of the data and the prior. Yeah. Okay. So this property that I was mentioning, so by the property of iterated expectations, okay, what we get is that we can write we want to work on, we want to understand this guy, right? So the other guys are just simple. But that guy, the middle term, can be written in 2 ways depending on, or using this property of iterated expectations. So what is this? Well, we just say, well, let me first of all take the expectation with respect to the prior, or the posterior, excuse me, I said, yeah, okay, so this is with respect to the posterior, of course, because, yeah, okay, let's leave it as this. We've already defined this expectation, and, earlier we sort of looked at exactly this quantity. Yeah. Okay, so we can write then the expectation of this theta delta x with respect to the posterior, and then take the expectation with respect to the x, right? And what is this? Well, this is going to be, because the delta is not going to be integrated, then we could take it out. And so if we take now the expectation of the theta, then actually it turns out that that should be precisely the pi base rule, right? What is left. Why is that? Well, that's because of this example sheet result that we were talking about. So in the example sheet result, I remind you that it says that the unique pi base rule for this quadratic risk is this guy in here. Yeah? And that's the guy exactly that we would get by taking the delta out. And so, yeah, so that's actually delta. Yeah, okay, so this is then, because we're assuming in this theorem that we have a pi base rule. That's actually the only one. Yeah? Okay, so we get this squared, and then let me now take the expectations in the other order. So we're now going to take this quantity, and what is this? Well, we can take the theta out, and so if we take the expectation with respect to the probability distribution of the data of the decision rule, then what do we get? Well, we assumed that we have unbiasedness, so this is going to be theta, and so essentially this is going to be the expectation of theta squared. Yeah. And now in here we have 2 terms, right? We have 2 of these, so we can, one of them substituted by this one, and then the other one substituted by this, and then you get exactly 0. So that shows the result. Yeah. Okay, so then just a quick remark about this. So what do we have? So we just said something quite special about unbiased estimators, right? So unbiased estimators are going to be, and this is typically so they're going to be, as a family of estimators is disjoint from Bayes estimators. And this, of course, for the quadratic risk. Okay. So in the example sheet, you will show the following. I don't want to say that. This is just example sheet. You get the following. So you prove a couple of results. So if we take, if we take the delta. So if we take the delta to be the theta MLE in the following model, so we have the model that we've been considering so far. Remember, we have this unknown mean and unrestricted and known variance that's actually equal to 1 without loss of generality, just by rescaling if you wanted to. So this is not. It's not Bayes, yeah, for any prior. Okay, that's important, right? Because the MLE is not going to be Bayes, and so this will, okay, so that's what it is, and this has to do, as we just said, with the unbiasedness, right? So actually so we've already seen an instance in which, it could be that bias is good. So I remind you this, we talked about in the Kramer-Rao lower bound, and we said, well, actually it may be possible to improve upon this sort of lower bound for the constant of the variance, basically, of the estimator by having unbiased estimators. And so here we again see an instance of the fact that even though unbiasedness is a very sort of natural quality or property of estimators, it may not always be, preferable. And, these observations have been made towards, the second half of the 20th century. And then this takes us to this bias variance trade-off that actually tells you that you may be better off in terms of risk if you bias your estimator a bit, yeah? If you do it properly. Okay, so let's now give a second example. So this is going to be let's say so x over n in a binomial model with parameters n and theta, so n is known, of course. And we say that this is not Bayes except in degenerate cases. So essentially, and this is why we said typically, so essentially any non-trivial example or any non-trivial unbiased estimator cannot be a Bayes estimator, okay, for any prior under the quadratic risk. Okay, so we'll continue with this decision theory in the next lecture, and I hope to see you all there.